So let's go ahead and finish this chapter up. So 5.5. Can everybody see elasticity of demand?
Yeah.
Okay, thank you. So we've already done plenty of equations and worked with the demand function before. Well, this time we're working with something called elasticity of demand, and that's given by this equation right here. So we need the original demand function, we need the derivative of the demand function, and then minus 1 over x. And that'll give us this quantity that we're talking about. Another relationship that we can look at is the revenue. So we all know that the revenue is x times the demand function. And if we want to talk about marginal, right, that means take a derivative. And so that's because this is a product between two functions, right, we would get d of x plus x times d prime. And then using the relationship for E, we could take and solve this equation for x d prime, which basically just means switch it with that E there, which gives us this equation. We could then take that and substitute it into the revenue equation. And so we get an equation for the marginal revenue that looks like this in terms of the elasticity of demand. Now, why is that important? Well, it says here, if this E quantity is greater than 1, well, then you'll find that R prime is greater than 0. So let's think about that for a second, right? If I let E equal 2, for instance, so 1 minus a half, that's a half, and we get something greater than 0. And if R prime is greater than 0, well, we know that really means that the revenue is increasing, right? Because the derivative is positive. And then they also call this elastic demand. We can also have a situation where E is less than 1. And if that's the case, then this number in here becomes negative. Right, so if we said maybe let E equal 1/2, for instance, 1 divided by a half is 2, and then 1 minus 2 would give you -1 in there. So that would make the whole value of R prime negative. And we know if the derivative is negative, it's then decreasing. And we can also call this inelastic. And then finally, there's a case where E equals 1. And if that occurs, then R prime is 0. And we know that for the first derivative, if we get back a 0, then we're getting either a maximum or a minimum. So in this case, we'd be getting a maximum. And we call that unit elasticity. So these names are just there because they might ask you, well, what kind of elasticity of demand do you have? And so you would just state those. That's really all that's for. But this helps us not only use, right, the idea of derivatives, but apply it quite a bit to these situations. So let's go ahead and look at some of these problems. The first one here says, suppose that the demand function is given as 300 minus 2x. What is the price per unit if 50 units are sold? Well, that's nothing more than plugging in 50. So d of 50, that's 300 minus 2 times 50, or 300 minus 100, which is 200. Real tough stuff. Next part says, find the function describing the elasticity of demand. Well, as above, that was described as minus 1 over x, d of x divided by d prime. So we just need to find d prime. So d prime, which will be the derivative of this function, is going to be minus 2. Plug it all in. So d is 300 minus 2x all over minus 2. The two negatives multiplied together there would make it positive. Then we'd have 300 minus 2x over 2x. You could leave it that way, or you could write it as 150 over x minus 1. Either one of those, I think, would be acceptable. The last part says, can we find the, I'm sorry, part C says, can we find the elasticity for 50 and 110? Of course we can. We've got E of 50. It's 150 over 50 minus 1. And that's just going to be 3 minus 1, or 2. And so someone might say, well, what kind of elasticity is that? So if we scroll back up here for a second, the elasticity greater than 1 is elastic. Right, so this number is greater than 1. So this is elastic. And what about E of 110? So I'm going to plug that in. So this would be 15 over 11 minus 1, or 15 minus 11 all over 11, which is 4/11. That, however, is less than 1. So for the less than 1 case, we are inelastic. Last part of this problem says, what quantity X maximizes revenue? So we can do this a couple different ways. I think that the easiest way, it says maximize revenue. So that means R prime has to be 0. So we could go all the way back up here and we could find R prime, or we could recall that R prime here is given by dx times 1 minus 1 over e. So maybe let's do it both ways. Let's do it this way first. So it's dx times 1 over 1 minus e. Now, this does say for R prime to be 0, e should be 1. However, if we do that, that means that this thing is 0, right? So let's plug in. We want 300 minus 2x, that's d. And then we have 1 minus 1 over. Now we've got e which we had up here. I'm going to write it in the 300 minus 2x all over 2x form. Okay, so next I would distribute this whole set of parentheses to both terms. And actually, before I do that, 1 over a fraction means I can rewrite the fraction. Of course, now my erasing ability has just decided to stop. Oh, there it went. Okay. So this should be 2x over this. Everybody okay with that? All right, if e is equal to this guy, then 1 over e is just the reciprocal. And then if I distribute, this would be 300 minus 2x times 1, so that you get back itself, minus, or actually we have negative times negative, so it'd be plus, and the 300 minus 2x times, I'm sorry, this would be minus. There we go. All right, so we'd have 2x times, or 2x over 300 minus 2x times 300 minus 2x. And so in that case, these two terms would cancel, and we would just be left with minus 2x. Let me go ahead and just write it out so you guys don't know what I'm doing. I guess it's all my jumbling of words there might have confused someone. So I'm doing it like this. So I'm just multiplying the parentheses by both terms. And so in this case, these cancel. So left behind, I have 300 minus 2x minus 2x, and this has to be 0. That then gives me 300 minus 4x is 0. Solving for x, I get 75. So everybody good with that? Sloan, did you want to say something? I see your mic's not muted.
Oh no, I didn't realize that it was.
Oh, no, you're fine. I just checked. I'm trying to see if anybody's trying to say something and I can't hear them, that sort of thing. So I assume you guys are okay with that. If you're not, please say something. I will continue on to the next example. So problem number 7. Product is known to have a demand function. Again, given. Find the value of x for which e equals 1. Okay. So again, e is equal to minus 1 over x, d of x over d prime of x. So we need d prime. So does somebody want to tell me what the derivative of d is there? Or at least give it a try. Now, you guys are all being really loud. I can't hear it one person at a time, so I guess I'll help you out here. 100 stays. Then we've got, for the exponential, we just bring down that number, so minus 0.5, and then leave the exponential. So minus 50 e to the minus 0.5x. So e, if we plug everything in, it's minus 1 over x. D is equal to 100 e to the minus 0.5x. D prime minus 50 e to the minus 0.5x. That's nice because these exponentials cancel. And then, of course, 100 over 50 is just 2. And the two negatives give us 2 over x. Now, we were told that e equaled 1. So we just set this equal to 1. And so x equals 2. So not a whole lot there. Just take a derivative and then substitute in and do some manipulation. So again, for part B here, we're asked to maximize the revenue. So I thought this was an interesting question because we could go through all that difficulty again. However, we're told E is 1. So if we paid attention, back up here, we said E is 1 is in fact where the revenue is maximized. So we don't have to do anything else. We just need to use that fact. X is 2. And it looks like when I worked this out the first time, I'll need to make a change. I accidentally made this that guy. So I need to fix that for you on the Blackboard page. We okay with that one?
Yep.
Okay. All right, I believe this is the last problem in this section. So grocery store determines that the demand function for its bakery's bread is this equation, where X is the number of loaves of bread it sells daily, and P is the unit price. Find the quantity demanded when the price is $1.70. Well, that's, again, very simple. We just need to plug that in. So we have 180 minus 30, and the price is $1.70. So that's 180 minus 51, which comes out as 129. Part B asks for a function describing the elasticity, but they want it as a function of P. So let's write out elasticity again. Minus 1 over x, d of x over d prime. So recall that P is equal to d of x. So this is really minus 1 over x, P over P prime. And so P is also a function of X. So if we take the equation that we were first given, we can solve it for P. Right, we can subtract 180 and then divide by negative 30. So we get P equals, and we can just flip it around and make it 180 minus X over 30. So if we want the derivative of P, or P prime, well, that 180 over 30 term goes away. But if we really want, we could maybe rewrite P here. That would be 6 minus X over 30. And so P prime, right, the first term is a constant, and the second we would just get minus 1 over 30. So plugging everything in, this would be minus 1 over. Now X is equal to this. So that's 180 minus 30P, right? Because we want everything in terms of P, times P over, and P prime is minus 1 over 30. Simplifying, we have two negatives, which makes the whole thing positive. Dividing by 1 over 30 means I can just multiply by 30 all the way on top. And so I have that. And if I want to, I can divide everything there by 30. And end up with this equation. That would be the elasticity in terms of price P. The next part says find the elasticity for P equal 1.7. So plug that in. And give me just 1 second. Make sure I get this fraction correct. So we're dealing with some, looks like prime numbers here. Darn it. All right, so it's 0.3953488372. That number is clearly less than 1. So this is inelastic. And again, I noticed I made a mistake on the notes I sent out, so I will fix that as well. Everybody hanging in there so far?
Yep.
Okay.
You.
The last part, determine the revenue function R and to find P so that R is a maximum. All right. So we've got R prime is equal to d of x times 1 minus 1 over e. We can rewrite that in terms of p. Right, d is equal to p. And we have e in terms of p as well. Right, e was p over 6 minus p. So anytime we do 1 over, we're basically just going to get the reciprocal, right? So this is p times 1 minus 6 minus p over p. R prime then is going to equal, if we distribute, p minus, very important that you put parentheses here, 6 minus p. So R prime is equal to, this is going to be 2p minus 6, because this is negative times negative here. Now it says we want R to be a maximum, which means we need R prime to be 0. So solve this for p. That's pretty easily 3. And then we want, let's see, is there anything else? It says determine the revenue function R and find P. So R is just going to be x times d of x. That's x times p. And if we go all the way back, x was equal to 180 minus 30p. So you should also be able to take the derivative of that and solve. So I'm curious, let's find out. R prime, I'm going to take out a 30 out of that. Actually, there's no sense in doing that if I'm taking the derivative. So derivative, the p on the outside is 1. So 180 minus 30p plus, leave the p on the outside, derivative of the inside is minus 30. So this is, now I can factor out or just work with the numbers. Probably confuse you less. Minus 60p. We want this to be 0. 60p equals 180. Divide through by 60. So p equals, get rid of the ones, 18 over 6. Would you look at that? So either way works. This is your revenue function, and these are your price P in order to maximize revenue. Good with that? So I only have about 2 minutes left on this meeting. I'm going to stop sharing and stop recording.